Hey everyone, and welcome back to Thinker's Factory. Today we're going to be talking about vaccines and their history. Vaccine: suspicion of weakened, killed, or fragmented microorganisms. It can also be toxins of antibodies or lymphocytes that is administered primarily to prevent disease. A vaccine can confer active immunity against a specific harmful agent by stimulating the immune system to attack the agent. In other words, it trains your body to fight against diseases. Once stimulated by a vaccine, the antibody-producing cells called B cells remain synthesized and ready to respond to the agent should it ever, and I mean ever, gain entry to the body. A vaccine may also confer passive immunity by providing antibodies or lymphocytes already made by an animal or a human donor. Vaccines are usually administered by injection, but some are given orally or even nasally. Vaccines applied to mucosal surfaces such as those lining the gut or nasal passages seem to stimulate a greater antibody response and may be the most effective route of administration. The first vaccine was introduced by British physician Edward Jenner, who in 1796 used the cowpox virus to confer protection against smallpox, a related virus, in humans, as he noticed that people who milk cows rarely get sick with smallpox. Prior to that, however, the principle of vaccination was applied by Asian physicians who gave children dried crusts from the lesions of people suffering from smallpox to protect against the disease. While some developed immunity, others developed the disease. Jenner's contribution was to use a substance similar to, but safer than, smallpox to confer immunity. He thus exploited the relatively rare situation in which immunity to one virus confers protection against another viral disease. In 1881, French microbiologist Louis Pasteur demonstrated immunization against anthrax by injecting sheep with a preparation containing attenuated forms of the bacillus that causes the disease. Vaccine effectiveness. After Pasteur's time, a widespread and intensive search for new vaccines was conducted, and vaccines against both bacteria and viruses were produced, as well as vaccines against venoms and other toxins. Through vaccination, smallpox was eradicated worldwide by 1980, and polio cases declined by 99%. Other examples of diseases for which vaccines have been developed include mumps, measles, typhoid fever, cholera, plague, tuberculosis, and many more. Although some of vaccines are less than 100% effective or are used only in populations at high risk, vaccines against viruses provide especially important immune protection since, unlike bacterial infections, viral infections do not respond to antibiotics. The challenge in vaccine development consists in devising a vaccine strong enough to ward off infection without making the individual seriously ill. To that end, researchers have devised different types of vaccines: weakened or attenuated. Vaccines consist of microorganisms that have lost the ability to cause serious illness but retain the ability to stimulate immunity. They may produce a mild or subclinical form of the disease. Attenuated vaccines include those for measles, mumps, polio, rubella, and tuberculosis. Inactivated vaccines are those that contain organisms that have been killed or inactivated with heat or chemicals. Inactivated vaccines elicit an immune response, but the response often is less complete than with attenuated vaccines. Because inactivated vaccines are not as effective at fighting infection as those made from attenuated microorganisms, greater quantities of inactivated vaccines are administered. Vaccines against rabies, polio, some forms of influenza, and cholera are made from inactivated microorganisms. Another type of vaccine is a subunit vaccine, which is made from proteins, usually spike proteins found on the surface of infectious agents. Vaccines for influenza and hepatitis B are of that type. When toxins, the metabolic byproducts of infectious organisms, are inactivated to form toxoids. They can be used to stimulate immunity against tetanus, diphtheria, and whooping cough. In the late 20th century, advances in laboratory techniques allowed approaches to vaccine development to be refined. medical researchers could identify the genes of a pathogen that encode the protein or proteins that stimulate the immune response to that organism. That allowed the immunity-stimulating proteins to be mass-produced and used in vaccines. It also made it possible to alter pathogens genetically and produce weakened strains of viruses. In that way, harmful proteins from pathogens can be deleted or modified, thus providing a safer and more effective method by which to manufacture attenuated vaccines. Recombinant DNA technology has also proven useful in developing vaccines to viruses that cannot be grown successfully or that are inherently dangerous. Genetic material that codes for a desired antigen is inserted into the attenuated form of a large virus, such as the vaccinia virus, which carries the foreign genes piggyback. The altered virus is injected into an individual to stimulate antibody production to the foreign proteins and thus confer immunity. The approach potentially enables the vaccinia virus to function as a live vaccine against several diseases once it has received genes derived from the relevant disease-causing microorganisms. Vaccines against human papillomavirus are made from virus-like particles which are prepared via recombinant technology. The vaccines do not contain live HPV, biological or genetic material, and therefore are incapable of causing infection. Two types of HPV vaccines have been developed, including a bivalent HPV vaccine made using VLPs or HPV type 16 and 18 and tetravalent vaccine made with VLPs of HPV type 6, 11, 16, and 18. Another approach, called naked DNA therapy, involves injecting DNA that encodes a foreign protein into muscles. The cells produce the foreign antigen, which stimulates an immune response. Benefits of vaccination. In addition to the development of memory B cells, which are capable of triggering a secondary immune response upon exposure to the pathogen targeted by a vaccine, vaccination is also beneficial at the population level. When a sufficient number of individuals in a population are immune to a disease, as would occur if a large proportion of a population were vaccinated, herd immunity is achieved. That means that if there is random mixing of individuals within the population, then the pathogen cannot be spread throughout the population. Herd immunity acts by breaking the transmission of infection or by lessening the chances of susceptible individuals coming in contact with a person who is infectious. Herd immunity provides a measure of protection to individuals who are not personally immune to the disease. For instance, individuals who, because of their age or underlying medical conditions, cannot receive vaccines, or individuals who receive vaccines but remain susceptible. Herd immunity also played an important role in the successful eradication of smallpox, and it is vital in preventing the spread of diseases such as polio and measles. This is all for today. If you enjoyed the video, then leave a like, and if you are new, then do not forget to subscribe. See you to the next video, and thank you for watching.